So how do we detect? Oh, I mean, obviously, if you're at the epicenter, detecting an earthquake's pretty easy because you just fall over when it happens, right? But at a distance, how do we detect and then measure the size of a seismic wave? Well, we use a machine called a seismograph, right? Seismograph. That is the actual machine that does the measuring and recording of the earthquake itself. And this one here lives in the geology department over at Grand Rapids Community College. This is just a little tabletop version. It's about as large as a fish tank, basically, so not very big. Hooked up to a computer. And this is, a student model. Obviously, the professional ones that they use are uh, much more sophisticated. There's a one over at Calvin College, a real one that is dug down into a section of ground underneath the science building there, and that is actually one of the official seismogram recorders or seismograph recorders. So this one is just for lab demos, but still it's uh, sensitive enough to pick up a nuclear test about 3 years ago in North Korea. Well, actually, officially the USGS isn't the person that calls it a nuclear test or not. Uh, but it was an earthquake with a depth of 0, so you go figure that out. Anyway, but what we get from a seismogram or from a seismograph is a seismogram, right? It's like a telegram, right? A seismogram. This is the actual record that is produced by the seismograph, right? And back in the day, it would have been like the little barrel and the little needle going like this. Now it's all done by computer, obviously, but we can see the different types of waves here. So here's the seismogram record of a P wave arriving, right? You can see that it's different than the baseline, but not a lot of shaking. You can really tell the difference when those first S waves arrive, right? And then here's the surface wave. So you should be able to see kind of very dramatically from this example here, right? Where those different types of waves and the intensity of those different types of waves, right? So that's how we kind of we find the earthquakes and measure them using those seismograms. There's a couple different ways to measure that, which we'll discuss in a minute. Uh, but how do we locate an earthquake? How do we find the epicenter of an earthquake? Well, as I said, the P wave is the fastest of the waves. It travels the fastest. The S wave a little slower, right? So first of all, we need to know the speed of both waves in the material that they're traveling through. And we do know that. I personally don't know those numbers, but the seismologists know those numbers. Um, so we have those numbers, right? And then we determine the distance from that station, right? From that seismograph station to uh, to the epicenter of the earthquake, based on how long it takes between the arrival of the first P wave and the first S wave. Now remember, P wave travels faster. It's like your buddy running faster than you, right? Uh, and then S wave travels second fastest, right? So the farther you are away, the farther it has to travel. The farther ahead that P wave is going to get from that S wave, or you could also say the farther that S wave is going to lag behind the P wave, right? So the more time between the arrival of the P and the S wave, so 73 seconds here, 57 or 14, right? The longer interval of time between the arrival of the P and the S wave, the farther away the epicenter of that earthquake was, right? So this station here labeled ISCO, 14 seconds away. This is pretty close, right? This is definitely the closest of them, right? To get to this second station, it took 57 seconds, so it's obviously a lot farther away. Then to get to this third station, 73. So this is the farthest away of those stations from the epicenter, right? So again, the longer interval of time between that P wave and the S wave, the more distant that quake is, right? So now that we know the speed of both waves, right, and the time that they've traveled, right? The difference in arrival time. Using that information, we can put it into a formula and calculate, kind of exactly how far away the epicenter was from that individual station. So we'll take the 14 seconds here, we'll throw that into our formula, and we'll come out with a distance of X miles or whatever, right? Same thing with this, and same thing with this, right? But now we know how far away it is from that station, but we have absolutely no idea which direction it came from, right? Was it north? Was it south? Was it east? Was it west? Which direction did it come from? We have no idea. We just know how far away it was. So in order to figure out where it is, we're going to need to use at least 3 different stations, right? So if we look back here, here's our WUAZ, DUG, and ISCO, our 3 different stations, right? Farthest away, second farthest, closest. Now if we look here, we have those farthest away, second farthest, closest, right? Kind of plotted there, right? And what we're showing is you need at least 3 seismic stations. And this is the same thing with like, GPS for your car or your phone. You need at least 3 satellites to pick up that to do what's called triangulation, right? So now here's our station, right? We figured out the arrival time between the P and the S wave. We converted that into a distance, right? But we don't know what direction, so it could literally be anywhere on the circle. So if we just have one station, there are literally infinite possible solutions to where that epicenter could be. It could be anywhere along this circle, right? Now, if we add a second one, let's say we add this WUAZ in there, right? And we do the same thing. We plot that distance. We draw a circle around it because it could be anywhere around that circle, right? Now, these 2 circles intersect at this point and this point, right? So now we know from 2 stations that it's going to be either one of these 2 locations, right? So we've gone from 1 station, infinite possibilities around that circle, 2 stations where they intersect, right? That gives us 2 possibilities. And then we're going to take a 3rd station, right? Do the same thing, right? Where those intersect, those are the possibilities that we have, right? So where all 3 stations intersect, or where the circles for all 3 intersect, that is going to be the epicenter, the location of the epicenter of your earthquake. So looking at this circle, and this circle, all 3 of them intersect right at this spot right here, right? So this is the location of the epicenter, right? So the intersection of the 3 circles, that will give you the epicenter, right? So you need a minimum of 3 stations. You can have 27, 35, 160, whatever, that just, helps make you more accurate, but you need a minimum of 3 stations to locate the epicenter, right? Now, measuring the size of earthquakes is another thing we have to look at. So here is our world famous San Andreas fault itself. Whoops. Some slippage on there. We get an earthquake. We figure out the epicenter, right? But how do we figure out how large or how destructive or the impact of this earthquake, right? Well, we have 3 scales. We have one called the Mortality intensity scale. Another one called the Richter scale, which I'm sure is the one you're all familiar with, right? And then a 3rd one called the moment magnitude scale. So these are the 3 scales we have for measuring earthquakes. And the Richter scale and the moment magnitude scale are pretty similar. We'll talk about those in a minute. The first one we'll talk about is the Mercalli intensity scale. This is completely different than the Richter or the moment magnitude scale. So the Mercalli intensity scale, the first one, measures the destructiveness of an earthquake from 1, very weak and not felt by people, to a 12, total destruction, cars and houses and trees and dogs thrown into the air and all this kind of stuff, right? But really, this is a very subjective scale. It measures how an earthquake felt and the damage it caused. So, how did that earthquake make you feel? How'd you like it, right? What did it do to you? And that kind of thing. It's very subjective, right? Because it varies with populations, right? get a strong earthquake out of the middle of nowhere. Nobody feels it. It's going to get a pretty low ranking, right? However, you could have a pretty weak earthquake in an area that's got really crappy building codes. This happened in Haiti a few years back, 2010, I believe, something like that, where there's a lot of destruction, right, even though there's not a lot of energy release, because the building codes are crap and there's a lot of death and stuff as a result. So you could get a not very strong earthquake that causes a lot of damage, and it gets much higher ranking on the scale. So just to kind of show you the scale here, we have from 1 not felt by a few people, right, to 12 damage total, waves seen on the ground, objects thrown up into the air, right, and then everywhere kind of in between. The next type of scale is the one you're probably most familiar with, the Richter scale. And here we have the earthquake, size of the earthquake is based on the maximum amplitude of a seismogram. So that, that little needle that goes up and down, right? The higher up and down that needle goes, so the more wobble there is, the larger the magnitude of the earthquake, right? And the scale here is logarithmic. So this is, the other one would have been the moment magnitude, or the Mortality scale is a qualitative scale. The Richter scale is a quantitative scale, so we can use it to do math and stuff. And the scale is logarithmic. What do I mean by that? Is that each time you jump up one scale, so from a 1 to a 2, or 2 to 3, or 3 to a 4, you multiply the amount of ground shaking by 10 times, right? So, for example, think about a magnitude 3, right? A magnitude 4, right, one step up, would be 10 times more ground shaking than a magnitude 3, right? Now, a magnitude 5, right, so we have 3, right, 4, 5, right, that would be 100 times stronger than a magnitude 3, right, for as far as ground shaking. So each time you step up one, so magnitude 3, right, magnitude 4 is 10 times stronger, magnitude 5 is 100 times stronger, magnitude 6 is 1,000 times stronger, etc. Right? That's with the ground shaking, right? With total amount of energy released, however, it goes up by a factor of 30. So again, from a 3 to a 4, we go up 30 times the amount in energy release, right? Or a 3 to a 5, that would be 900 times the amount of energy release, right? For a magnitude 3 and magnitude 5, 900 times more energy release, 100 times more ground shaking in a magnitude 5 than in a magnitude 3, right? There's theoretically no upper limit to the Richter scale, until you get an earthquake so large it rips the whole planet into pieces. However, fortunately, that will never happen because there is a limit to the strength of the rock, right? Remember when we talked to how an earthquake works, it requires that, eventually a break happens and a fault happens, right? And when that fault breaks, the energy is released, right? Well, rocks are only so strong, right? So we will never get an earthquake that rips the entire planet in half, right? Moment magnitude scale, pretty much like the Richter scale, but this is a measurements preferred by geologists. This you have to actually go up to the actual fault, the place where the rupture occurred, the epicenter, right? And with your stick and your measuring tools, and figure out how much total offset, how much displacement actually occurred on that fault. And this gives you a better amount of estimating the total amount of energy released, especially in very large earthquakes. But it's not going to be that different from the Richter scale. So if it's like a 7.1 on the Richter scale, it might be a 7.2 on the moment magnitude scale. So they're similar, but just a little bit different as how you calculate them, right? It's also easier to verify because you just walk up to the fault with a measuring stick and figure out how much it moved, right? And then what I just kind of want to show you here are some different magnitude earthquakes, and we're going to also look at building codes here. So here's a 7.1 magnitude earthquake in Mexico City. So this is the same size that I showed you at the very beginning of the lecture when we talked about the California earthquake, right? And then I want to show you a 9.0 earthquake that happened in Japan. So 9.0, almost 2 levels up, 7, 8, 9, right? So we're talking 100 times more more ground shaking and 900 times more energy release in this Japanese earthquake. And I'll tell you why that's important here. But first of all, okay, fine.
Joe Biden tried to cut Social Security and Medicare for decades.
We should freeze federal spending. I meant Social Security.
All right.
I meant Medicare.
Hold on.
I'm Donald J. Trump, and I approve this message.
All right, here we go. All right, so this is again the 7.1 magnitude earthquake in Mexico City. Here they do not have very strict building codes at all in response to preparation for earthquake or mitigation against earthquake. So all this dust you're seeing here, the background, guess what that is? Those are collapsing buildings. So look at all the buildings collapsing. Right, you see all that dust. Give you a close up of one of those buildings collapsing. Here comes the source of the dust there. Just to give you an idea again here. Overview of the city again. Look at all the dust. All right, all the collapsing buildings. Fair enough. Okay. All right. All right. So that was. So that was 7.1 again in Japan, or in Mexico City, right? Whoops. Here is a 9.0 earthquake in Japan, and again, 100 times more ground shaking, 900 times more energy release. Hopefully you can see this. That's where it's similar. Can you imagine being a librarian? Okay, so this part here where these two pieces of road are snapping back together, this is also a type of earthquake mitigation for building. If they're gonna move and bend anyway, let them do that, but then have points where you can just elastically pull them back right to where they start. So this is designed to do what it's doing here. And then here's something else that I really want to show you here, folks, because along the bottom here, we have the seismogram, right? Showing you the different waves arriving, and it shows this as it plays the video in the background, so you can see the intensity. So here we're dealing with the primary waves, right? But it's kind of like, oh, shaking, right? Oh, shaking, right? But now here come the secondary waves. See the difference in intensity?
振り幅が一気に大きくなったこの時、震度は6弱を記録。この大きな揺れの原因が宮城県沖で で午後2時46分18秒に起きた断層破壊だった。
And then here come the L waves, or surface waves.
再び大きな揺れが襲う。この時の震度は断層破壊から42秒。
Here's an even better example.
断層破壊が起きたためだった。その結果、大崎市は2度の大きな揺れに襲われていたのだ。これは
So here's an even better example, more dramatic. So here come the P waves, those first waves. Then we'll see the S waves come, and you'll see a lot more shaking. And then we'll see the L waves, and you'll see just how intense those are. So here are the P waves, just kind of like come here, it's shaking a little bit, right? Here come the S waves, secondary waves. How much more intense that is.
突如襲った最初の大きな揺れ。この揺れは一度目の断層破壊が伝わってきたものと考えられる。さらにこの後、
And then here come the L waves, right, the surface waves. Mm.
第2の揺れが襲う。ここまでの揺れの回数は大崎市と変わらない。
So that's just kind of what I wanted to show you there. Hopefully you get the dramatic difference from those videos between the intensity of the shaking and these different types of waves, right? But one thing you did not see, video Japan, and next time I'll show you a little bit better video of this earthquake. One thing you did not see in Japan was collapsing buildings, right? So lots of shaking, 100 times more shaking, 900 times more energy release than the earthquake in Mexico City, but a lot more stringent building codes, so a lot less damage overall, right? So this would get a lot lower Mercalli intensity scale ranking than the earthquake in Mexico City, even though with as far as energy, it is much more intense, right?